Okay. So is everybody planning to stay for the full session, or does somebody have something before 8:30 and might need to head out early? Just let me know if so, okay? And no pressure to stay the entire session. Okay. So I'm going to wait until Chris lets me know that he started the live stream. Since we post these sessions on YouTube, okay? If you're interested in looking at past sessions, then you can look at CognitionTO, and you'll be going to the live tab, and you'll see some of the previous sessions which were held while Josh was being on this. Okay. We recently moved to a new office, which is part of the reason behind some of the live stream, behind the Wi-Fi issues. Normally, I make sure that it's all works reliably. But
so we're good to go. We're live.
So this isn't a full paper, okay? It's more of a research blog post from Anthropic, okay? And the authors are, Chris Olah is one of the authors. So I'm a huge fan of Chris Olah's work. And he's part of the inspiration for me to get into interpretability research, okay? And the second paper that we might get to, if we have time, okay, is by Liv Gorton, who is currently on vacation, but she works at Goodfire, which is a company founded by Eric Ho, which has raised a few $1 million to do steering in large language models. And I know, Shivam, your supervisor, the stuff with steering Fernanda.
Yeah.
Right. So I think that it's a small, and I was interested in Liv's paper because—
Which paper are you talking about?
The paper by Liv Gorton, which is the second—
group symmetry crosscoders paper.
Okay. I think that's something with people with a mathematical background might be able to appreciate better than me.
Yeah.
Okay. But I think that it's very interesting work, and I DM'd Liv, and she said that, hope that the reading group goes well. So I might share this.
She's super nice. We had a conversation when I was in SF like last month. Yeah, she's doing great work.
So one of the interesting things, and I skimmed over Liv's paper because it came out a week after Anthropic published this, and I know that she doesn't have internal access to Anthropic's works in progress. So it was very impressive to see how quickly she was able to put a full paper out, very quickly after they—
Do you want to hear the backstory of how that happened? Because I asked her how, because it is impressive.
Yes.
I wanted to know, but maybe we can get to that at the later point.
Keep that open as well in a separate tab. Okay. Group crosscoders for mechanistic analysis, isn't it?
Oh, actually, it's a small TLDR. She had a bunch of she had many conversations with Chris Olah at Neil's McIntyre workshop.
Yep, and she actually acknowledges him down here. Okay, at the very end, okay, she says, thanks to Chris Olah, I'm grateful.
Oh, okay, yeah. So that's what she told me, that all the stuff that she did with the Inception V1 stuff and this paper was because Chris was like, yeah, crosscoders are cool. Someone probably should do something with Inception V1 and SAEs, and she did it.
Yeah, I once shared a draft that I was working on with Chris for feedback, and he actually replied to me and he said, sorry, I'm very over capacity right now. I can't look at drafts. But Chris really, he's very approachable. And
yeah, I had emailed him with a sort of rebuttal on Liv's previous work on Inception V1 features and feature manifolds. And yeah, he was super responsive.
Mm-hmm.
Yeah, we had a conversation, Liv and I, on feature manifolds when we met.
So if there is some sort of confusion, okay, that you have while you're doing this reading group, make sure to bring it up. Okay, I'll try to answer it as best as I can. And if I can't answer it, and if Shivan can't answer it, okay, then we'll probably write to Liv. And if Liv can't answer it, we just escalate to Chris Olah. Okay, so I want to make sure that everybody is able to understand, the there's going to be a lot of confusion because that's very common in research. But if you have a specific, doubt that is there, I'll do my best to answer it. Okay, even beyond the scope of the session, right? Okay. So, where autoencoders, I'm going to start here. Where autoencoders encode and predict activations at a single layer, and transcoders use activations from one layer to predict the next, a crosscoder reads and writes to multiple layers. Okay, I think this is fairly straightforward. I don't have slides that I prepared because I have an important meeting tomorrow with the head of the Canadian AI Safety Institute leadership, and I've kind of put all of my actual document prep work into that. But I can draw this out if somebody wants to see the difference. But we'll see a figure about this very soon. Okay.
So I have a question. So it says transcoders use activations from one layer to predict the next. Can you just use the model to predict activations from one layer from the next?
How would you use the model to predict the next layer's activations?
You just run the model. You just do inference on the model. Like you must be able to calculate the next layer.
But then you need to run inference on the model.
Right. So essentially, it's a way to try to figure out the next layer without going through all the work of doing inference.
Yes.
Okay.
This is useful because if there's one paper which came out from one of called SAPS, where they train a linear they do linear regression and try to find if they can predict the effects of steering before they steer. So yeah, for a large model, if you want to during inference time is kind of too late. Okay, so yeah, crosscoders can be useful. So it's a way to predict it rather than measure what are the exact but does anybody have a better explanation than that? So I can just note this question down. So your question was, why can't you
I can say what's the value of crosscoders what's the value of transcoders as opposed to just doing inference on the model? And I guess you're saying it's a way to speed up model inference?
I can try to answer that. I think if you have read on sparse autoencoders in general, the whole idea of sparse autoencoders is to interpret certain features vectors at a certain activations level. Right? I think down below this blog post, they will sort of answer the difference between a sparse, an autoencoders, a transencoder, and a crosscoders. But the whole premise of an SAE is that you intervene at a certain activation level within the neural nets to extract what the model see, what features at that specific layers, right? So the idea of an SAE is that you only access that one certain layers, right? Whereas with a crosscoders, their proposal is basically saying that instead of having multiple SAE as multiple activation layers, we can probably train just one crosscoder to interpret features from multiple activation layers. So essentially, it's a one-to-one relationship converted to many-to-one relationship, if that makes sense. To basically extrapolate what the model sees, in terms of features.
Is it an autoencoder but with all the layers as inputs?
You can think of it like that. So crosscoder would just works as if multiple autoencoders. Autoencoder is you can think of it as a special case of a crosscoder. So crosscoder is more of a generalization of how we can train these smallers. So So
I know what an autoencoder is and a sparse autoencoder, and we've done a talk about that before. But what is a crosscoder from a definitions perspective?
It's a generalization of sparse autoencoders.
Yeah, they will probably explain it down below. So yeah.
Okay, but great to see this discussion so far. Thank you, Aaron. Okay, so here's some of the things which crosscoders are useful for. Okay, sometimes people think of features that are spread out across multiple layers. Okay, and so it can be wasteful to think of just thinking of a residual stream feature in one layer versus the next layer versus the next layer versus the next layer. So you want to see okay, this feature, if it exists in all the multiple layers, a crosscoder might be a good way to represent it rather than having to train an SAE per layer. Okay, so you can track persistent features through the residual stream. Later on, there'll be a diagram that shows this more clearly. So if it doesn't make sense for now, don't worry. Okay, it might make sense later. Circuit simplification. So if you think about automated circuit discovery, okay, then there might be some duplicate features from analysis. So this allows features to jump across many uninteresting circuit conditions and generally simplify circuits. I think in one of the previous paper groups, we looked at the superweights paper from Apple, and this was one of the hypotheses which we had, that what might be going on when you ablate one weight and this causes a huge reduction in loss might be that there might be a circuit in a model which skips many layers and goes from the first layer to the last layer and then stopwards. And this is a stopward circuit. So it just like turns off the stopward ablation circuit. And then you just have like a lot more inside the paper. But, so essentially to summarize, what we're saying is that crosscoders can be used for understanding such circuits inside models, okay, and find simpler representations than you would with other methods, okay. Model diffing, okay, so this is the reason that I had.
Is there just before we move on, Devang got a question?
Yeah, so this is just a general comment. So the way I think about circuits and like how the transformers work is that there is the residual stream that goes from input to the output, and at every layer something from the attention MLP, like the transformer block, gets added in at each layer. And now it might also happen that for certain features the model doesn't really need to add much information or needs to add a lot of information. So if you're looking at the residual stream at different points, there might be features that could change because stuff gets added in for that feature at a particular layer. For certain things, they might not be changed. And so certain features are just propagated as is, and certain features might be modified slightly. And so in my mind, I'm thinking of crosscoders as like trying to find these features which are either propagated further without any change or are slightly modified, because that's what I'm thinking of when Chris says like cross-layer superposition, because like the feature exists at multiple layers at the same time because there's no new information that is being added that changes that feature to some other feature. Does that sort of intuition make sense to others? Or if anyone has any other thoughts on that?
I understand that each layer is adding information and it might add more or less information, okay? And this is what attention determines, like what part of the context is relevant for predicting the next token, okay? I didn't fully understand the latter half of your explanation.
So I'm just trying to understand what a cross-layer superposition for a feature could look like. Like what does it mean for a feature to be distributed across different layers when every layer is doing some computation on top of the features that exist and came before?
So a summary of this question might be, what does cross-layer superposition look like? Right? Is that like a accurate one?
Yeah.
I think let's keep that in the back of our head and keep moving forward in the interest of time. But good question. Okay, model diffing. So there is, if you're interested and have a second screen and want to have a more interactive session, there is a reproduction of this work, which I linked to, which is from one of Neil's scholars, okay? And it's about crosscoders for model diffing. So there's a Colab online. Unfortunately, it doesn't work if you're on free Colab. You need Colab Pro because the model will just run out of VRAM if you run through it. But there's a crosscoder model diff notebook, which I went through for 4 hours with one of my friends when I was on a train trip to Ottawa, okay? To like somebody who was very, like this was in November. So crosscoders for model diffing, if you have this notebook up, we might be able to answer some of our questions by running experiments in real time, right? So when we get to this section of the paper, it'll be good for now, we don't really need to keep open this notebook, but this is something that is there if you want to use it. Okay. And I personally I'm interested in one research question for model diffing, which is what is the reason I was reading this paper. Okay. So there's some theoretical examples motivating crosscoders, and there's some experiments which are applying them to cross-layer superposition, which I've mentioned, and model diffing, which is what I'm interested in. We also briefly discussed the theory of how crosscoders might simplify circuit analysis, but leave results on this for a future update. Okay. So cross-layer superposition. According to the superposition hypothesis, neural networks represent more features than they have neurons by allowing features to be non-orthogonal. Okay. One consequence of this is that most features are represented by linear combinations of multiple neurons. Okay. I think everybody basically gets this, right? Instead of just having one neuron per feature, we have multiple, and then we add them together. So this is just showing you how that works. Okay. And at first blush, the idea that this kind of superposition might be spread across layers might feel strange. But if you think about it carefully, it's relatively natural in the context of a transformer with a reasonable number of layers. How much is reasonable? Like more than, so I think if you have like 3 layers, that's not reasonable. If you have like 30 layers, that is reasonable. And if anything between 3 and 30, it depends on the opinion of the researcher. Okay. Yeah.
But I imagine they're looking at a model with way more than 30 layers.
Not necessarily, because if you look at like 70 billion parameter model,
Yeah,
it has like 35 layers.
I mean, Anthropic is not saying how many layers there are, but I assume that something like Claude 3 Opus would have like 80 layers.
Claude 3 Opus is going to be significantly larger than Llama 70B. Okay,
Oh,
Llama
okay.
70B is like, what I was referencing.
Yeah, because it says they're doing it on Claude 3 Sonnet later, and I assume that.
That information is not public. If you do know it, keep it to yourself.
Yeah, no, I don't
Yeah.
know. I'm just pure speculation here, but in my head, I imagine that it was a number around 80, but I don't know what the actual number is, and I'm not revealing any confidential information yet.
When I was at Microsoft, we did have access to the source code that was used to train GPT-3. Okay. And I did like get some information on like the GPT-4 code base.
Okay, I don't want to accidentally
But
make you say something.
so I know that what it's like for frontier models.
Okay.
Okay, but of course I can't share that.
Right, okay, you know what, I'm not gonna.
Don't send the Microsoft lawyers after our YouTube video.
Yeah. So one interesting property of transformers is that because the residual stream is linear, we can draw them as different equivalent graphs. Okay, so I'm not sure what is exactly meant by graphs here. Okay, like, is this just is this diagram a graph, or are they referring to like a computational graph?
I think he might just be thinking of every computation, like even attention head or anything, as sort of like a node link in the graph.
So you have data that is passing through the network, and then the network is doing computations on it. And instead of thinking of it as matrix multiplications followed by nonlinear operations, you are thinking of it as attention heads reading and writing through the residual stream. And so these are the nodes inside the residual stream, like the attention heads. Okay, that makes sense. So the 2 layers can be thought of almost parallel branches, except they have an extra edge that allows the earlier layer to influence the later. Okay.
I think the big thing to take away from that graph is that the path that goes through both blocks, it's there, but it's dashed out. It's not considered the primary flow of information. Most of the information will go through one or the other.
Yeah, so there's some sort of skid connection, right? Okay. So because the residual stream is additive, adjacent layers can be thought of as almost parallel. Extra path for the first. If you consider a one-step circuit computing a feature, we can imagine implementations where a circuit is split across 2 layers, but it functionally isn't parallel. Okay. This might actually be quite natural if the model has more layers than the length of the circuit is trying to compute. Okay. So one example of a long circuit might be if you are having I can't think of an example for a long circuit.
I have a quick question on this.
Yes.
So basically the proposal here seems like, or at least like from this graph, they propose that like, oh, because like each layers has sort of like a partial elements of a, we can call it like a meta features, right? So they say here superposition spreads the features over the neurons, right? And then each of the layers would probably have like just like a partial elements of this sort of like meta features. So what's like, would it be like more beneficial if we have the control over, I guess, like the smaller like partial features rather than like having like access to like the whole like internal big like features like this, if it makes sense? I guess like I'm just trying to understand like what is like the reason behind like having to like compose like each of these like features at different activation layers together.
Mm,
I would imagine the reason, like the motivation for doing that is something we're about to get into.
so what's the reason that we need to compose activations?
Right, yeah.
Okay. I'm not sure. Let's see if they talk about that later on in the paper. Okay. If features are jointly represented by multiple layers, where some of the activity can be understood as being in parallel, it's natural to apply dictionary learning to them jointly. We call this setup a crosscoder, and we'll return to it in the next session. Okay, so this is just introducing what a crosscoder is. Okay. So
Yeah.
worth noting that joint applying dictionary learning to multiple vectors is precisely what we do when models literally have parallel branches with cross-branch superposition. Okay. So what's the difference between cross-branch superposition and cross-layer superposition?
I think the branches are when the layers have earlier layers as inputs, but I'm understanding this to be that the branches are the layers using only the skip connection and just like glossing over and omitting the dependent layers. Right? So if you scroll up for a sec,
Yes.
a little more to this gray one, right?
Mhm.
So we have the skip connections, and each layer has the original input as part of its input. And so what I'm reading this, what I'm interpreting this to mean is that we're modifying it so that the layers, instead of the layer depending on the previous input plus the skip connection, we can turn it from a layer into a branch by making it depend only on the skip connection. And that becomes useful, I would imagine, for what they're about to do with the cross learning. But the way that they have that dotted one, it says, that to me says, yeah, because the residual stream is additive, adjacent layers in a larger transformer can be thought of as almost parallel with an extra path for the
Almost
first
parallel
layer.
into fully parallel.
What was it?
And you make the almost parallel into fully parallel?
That's what it says here. I'm just reading that. It says almost parallel with an extra path.
Okay, yeah.
That's why I'm reading it. I don't know if everybody's on the same page with that.
Persistent features and circuit complexity. Okay, so now we can see the crosscoders help us understand when there's cross-layer superposition. Okay, and they also help us understand when a computer feature stays in the residual stream from many layers. So you can think of this hypothetical feature lifecycle through the residual stream. Okay, so think of this as your model. Okay, and you have your MLP blocks and your input output. Okay, so at the early layers, the feature might not yet be computed. Okay, and in the intermediate layers, a feature is formed by cross-layer superposition. And then once it's formed, it stays inside the residual stream. Okay, and at one of the layers, you might have an amplification of that feature. Okay, so it's represented more strongly. And then it continues to be represented, and then it fades or is actively removed. Okay, Now, this is just one hypothetical life cycle. There can be other ones which have different shapes. Okay, I think this is just for illustrative purposes. Okay, sure. Go ahead.
Yeah, so when I was looking at this, I was a bit confused when they say that the feature is not yet computed. Like, what does it mean when the feature is not yet computed or has not been formed? Like, what is it then? And what does it mean to form a feature? If like features are things that exist in the model already, but what does it mean when it isn't formed or formed?
I think what it's saying is like there's this interesting property of the input text. And the model, like say, one interesting property is that it's rhyming with the previous line. And like at some early layer, the model doesn't know that. Like the model has not computed, oh, this line rhymes with the previous line, right? And then at some layer, in this example, the third one, the model, the weights of the model would be computing the fact that yes, this line does rhyme with the previous line.
Yeah, I think one intuitive way to think about this is if you think in terms of CNNs and edge detection, right? So earlier layers in a CNN might represent like more basic features, whereas later layers might have compositions of the previous, like,
Okay. If I'm drawing a parallel to CNNs and thinking about like compositionality there, then it makes sense. But for language, it could be just a concept that the model has not figured out at an early layer, right?
Yeah. Okay. So if we had tried to understand this in terms of a residual stream across at every layer, we'd have lots of duplicate features across layers. This can lead to circuits which seem much more complex than they need to. Okay, so now they're going to give us an example, okay, in which features 1 and 2 are represented by layer L, and they're combined to form feature tree by MLPs in layer L plus 2 and L plus 3, and then all 3 features persist in layer L plus 4. So on the left panel, we see, and this is the left panel, per layer essays will produce 13 features in total, corresponding to features 1, 2, and 3 at each layer represent. Causal graph relating them as many arrows. Okay, most for persistence. The feature causes itself in later layers. And this is what we mentioned earlier with this. And 2 for each stages in which the feature is computed, 1 and 2. An ideal crosscoder picture on the right would have just 3 features and a simple causal graph. Okay. So earlier series train on a residual stream. Crosscoders unify features across layers. This can potentially simplify circuits. So this means that crosscoders may also give us a strategy for adequately simplifying circuits if using an appropriate architecture where, as in the above picture, feature encoders read in from a single residual stream layer and the decoders write out the downstream layers. Okay, so let's try to understand this. Okay, this is the causal graph. So you have a model with per layer SAEs, okay, and this is before crosscoders, and you have the same feature, okay, and this feature exists in all these layers. This feature also exists in all the layers, and then this feature only exists in these top 3 layers. Okay, and does that make sense so far? Any questions? Okay. So if everyone understands, moving on, we have with crosscoders, we have the features which are in all of the layers grouped together. And we have this feature, which is only in 3 layers by itself. So then this is the circuit which we finally come up with. 1, 2, 3. Okay. So this was the circuit without crosscoders. Okay. And this is the circuit with crosscoders. It's a lot simpler. Okay. So features which are there in a common set of layers get unified. Okay. And feel free to also chime in on the chat. Okay, I see that Aaron had shared the SAE for Llama, and I'm monitoring it along with anybody raising their hand. Okay, so now let's move forward. This means that crosscoders may also give us a strategy for radically simplifying circuits if we use an appropriate architecture where, as in the above picture, feature encoders read in from a single residual stream layer and decoders write out to downstream layers. Okay. And as an example, suppose we have feature I, whose encoder lives in layer 10, and feature J, whose encoder lives in layer 1, but whose decoder projects to all subsequent layers. Okay. So let's try to draw this out. Okay. So we have, let's see, these layers. Okay. And there's the encoder and the decoder from that layer. Okay. So we can draw it over here. Sorry, I'm not used to drawing on this. Usually I have a drawing tablet, but it's not with me right now. And we're saying that the decoder doesn't just write to like this decoder doesn't just write to this layer, but it writes to these as well. Is that accurate? Or is there something wrong with this picture?
Can you tell me again what the big and the small blocks are?
So let's say that this is the layer. Okay. And then you have the encoder. Okay. W-enc. Okay. And then you have W-dec. Okay. So you have the weight encoder and then you have the weight decoder. So the idea is that you that the encoders read from a single residual stream layer, but the decoders, okay, they are writing out to downstream layers. So the earlier the layer is, okay, the encoder just reads in from the previous layer, but the decoder might write to multiple downstream layers. Okay. So if you want to look at this inside the, let me stop annotating for now. Okay. How do I stop annotating? Give me a second. I think cursor. Mouse. So if you go up here, you can see that that over here you have the writing and the reading. So 2B. So you only have one input, but you have outputs to multiple things. So you can see over here that the encoder only reads from at one point, but the decoder, which is the arrows which are going out, are going to multiple points. So does this make sense? This is a lot clearer than my
Yeah. So one thing I'm thinking about, if I'm thinking of the normal SAE, it reads out and projects back to the same point in the residual stream, which is why you can like do the training, because you can have the loss as reconstructing the activation back, and you're like projecting out into a over complete basis and back into the same residual stream. Now, if you're saying that you are reading it from one layer, projecting the same set of features onto another, how does the loss work for the crosscoder case? I just don't know, because I haven't gone through the whole thing in a while, but that's something to maybe note. Like, how do you even train a crosscoder? Because like reconstructions don't make sense.
There's another diagram a little further down that answers that.
Okay, let's keep going then, and we can answer that.
There's this equation.
Let's just answer it right away if we can answer it right away.
So this is the one that I was thinking of here.
Okay. Yeah, what are we looking at?
So we have where autoencoders encode and predict activations of a single layer, and transcoders use activations from one layer to predict the next. A crosscoder reads and writes to multiple layers, subject to causality constraints we may wish to impose, which we'll discuss later. This general idea of a sparse coder operating on multiple layers is also explored in forthcoming work. We can think of autoencoders and transcoders as special cases of the general family of crosscoders. So it's like you were saying, the autoencoder is specific to one layer, the transcoder takes one layer and predicts the next through its features, and then the crosscoder is just a generalization of that that's looking from multiple layers and predicting to multiple layers given constraint.
Hmm. So did that make sense, Shivam? I don't think you mentioned how this deals with the loss. When you
Yeah. So that part I still haven't gotten. Like, what would be the loss
It's a
like?
reconstruction loss, but it's just the autoencoder is reconstructing its input. The transcoder is reconstructing the next layer.
Oh, I see. I got it. Yeah, so it's not the reconstructing the activation at this point, but at like whatever point of the residual stream you are training the crosscoder on.
Yeah.
Okay, yeah, that makes sense. Thanks.
So we compute the feature activations on a data point by summing over contributions from the activation of different layers for layers L in. Okay, so we have this real activation function summing over all of the layers. Okay, and they add a bias. Maybe in some architectures you don't use the bias. Okay, where WL encoder is the encoder weights at layer L, and ALXJ is the activations of the data point XJ at layer L. So when we then try to reconstruct the later
When we say
activation,
encoder weights, are we talking about the weights of the model we're analyzing, or the weights of like the encoder we're making?
I think the encoder weights here refers to the crosscoder.
Okay, yeah, that's what I expected. I just
Yeah.
want to make sure.
So the weights inside crosscoder. Because if you look at this one, okay, the encoder versus the decoder. Okay, so yeah. So this is because this is a basic setup, of course. But good question. Thank you, Sneha. Okay. We then try to reconstruct the reactivations with approximations A, L, delta. Wait, how do you pronounce this? Like AL quote?
Prime, AL prime.
AL prime, yeah, okay. AL prime XJ of the activations at layer L. So AL prime of XJ equals WL decoder F of XJ plus BL of decoder. So the intuitive understanding is like, this is just the difference between how encoder and decoder are constructed inside the crosscoder. Okay. And so this is the loss, okay, that is there when you're training crosscoder. So Shivam, take a look at this. Okay, you have
Does that mean squared error?
Yeah, that's the mean squared error between the layer it's projecting from and to.
And
the one
reconstruction.
there is
This is
And
for
then that-
sparsity, I guess.
Well, they have the mean squared error. That's the first term.
Yep.
Yep.
And then that looks like a regularization term on the weight of
Yep.
their.
This is the, yes, so this is the mean square loss and this is regularization, but you can rewrite this, okay, and do it over here as this. So
That is, we weight the L1 regularization penalty by the L1 norm of the per layer decoder rate norm. Where the sum
Yeah,
of
I think he just switches the summation which you can do because they're like independent. Like summing of the weight columns for the decoder is independent of the function, whatever the regularization function is for the feature. So you can just do them independently and then product them together.
Hmm.
This
Okay.
is equivalent to treating all the decoder weights as a single vector and weighting by its L2 norm, which might seem like a natural thing to do.
Mm. Sorry, I just accidentally made the chat too big. Okay, it's back to normal. So they weight the L1 regularization penalty by the L1 norm of the per layer decoder, and so WL decoder is the L2 norm of the single feature decoder vector at a given layer of the model. Okay. So in principle, one might have expected to use the L2 norm of the per layer norms, but this is equivalent to treating all the decoder weights as a single vector and weighting by L2 norm.
Yeah, so all it's trying to do is just say that for each and every layer, everything should be unit normed, but all the features together shouldn't be unit normed. Something like that.
Mm-hmm. Yep.
The exact opposite of that. Like all the layers together should be unit normed, not just per layer unit norm. Like the features from each layer don't need to have a unit norm, but in total aggregate, all the features across all layers should have a unit norm.
Why?
That is what he says, I think, but someone can correct me if I'm wrong.
Okay, so let's see.
I think it comes from the idea of generalizing an autoencoder on each layer. So he's saying if this idea of a sparse autoencoder for each layer works, if you grant that, then this is the math that we can use to grant it for a crosscoder that's looking at all the layers together. I think that's kind of what we're getting at through here. Is a lot of it is coming from the perspective of, yes, we can use sparse autoencoders, therefore we can use the crosscoders. And that's why a little bit it seems kind of relatively simple core ideas, but it's reaching them from the starting point of sparse autoencoders per layer and trying to
Weight
generalize.
penalty by the norm of the per layer decoder weight. Okay. And what's the, okay, so this is the L2 norm. Okay. And they're taking the L1 norm of the L2 norms.
The L1 norm of the sum of the L2 norms, isn't it?
Okay. Yeah, they're taking the L1 norm of the sum of all of the per layer norms.
Yeah, so it's just saying that if we just look at the L2 norm of per layer norms, in total, the decoder weights norms per layer, if this is the term that we're looking at, like the 1 under square root, that just means that for every layer, whatever features are activated, only they would have unit norms, or only they would be regularized. I think either. I think, yeah, only they would be regularized. But we need all the features to be regularized across all layers.
So they're doing the L1 norm, but instead of taking the L2 norm of the per layer norms, right? So they're taking this approach rather than instead of this approach.
Yeah. As a reminder and sanity check that I'm actually remembering it right. The L1 norm is essentially the absolute value, and the L2 norm is essentially the square. Right?
Yeah, it's like if you have
and so they use the L1. The L1 is good for sparsity because regardless of how close it is to zero, it still pulls it towards zero. But the L2, it has that parabolic curve that when it's close to zero, it's the rate at which it is pulled to zero slows down. So you're more likely to get a true sparse result in the sense of a sparse autoencoder if you use the L1, and the L2 is used to get a a smoother result that pulls things close to zero, but as they get to zero, they stop getting pulled to zero as much, which means that you don't get sparsity the same way.
I think you can think of L2 as it basically just reduced the weight to near zero, right? Instead of like exactly zero, like L1. So
Yeah,
yeah, so rich or like L2 regularization is usually more better for feature in interp for like higher nonlinear, right? Whereas like L1, like you just like add like objectively like any sort of like penalty term. So yeah.
Mhm. So they're saying that there's two reasons to prefer the L1 norm version. Okay, and I think this might be what you are referring to, because in interp you have you're trying to address the nonlinearities. Okay, so let's see if they mention that baseline norm comparison. So the L1 of norms version enables apples to apples loss comparison between crosscoders and single layer SAEs. Loss of a crosscoder is directly comparable to the sum of losses of per layer SAEs trained on the same set of layers. So if you go back up here, you have per layer SAEs versus crosscoders, and you want to compare them, okay? And they're saying that the L1 version allows for an easier comparison between these two versus the L2 version, okay?
I think, why don't we go over those two bullet points? I was saying, why don't we go over these two bullet points? I think it answers the questions we were just discussing.
Okay. So if we instead use the L2 of norm version, crosscoders can obtain a much lower loss because they would get a bonus by spreading feature across layers. Okay. L2 version encourages features to be spread out across layers. Marginal increase in L2 of norms by allowing a feature to reconstruct more layers is decreased once the feature already has non-trivial decoder norm in other layers. The L1 of norms version, by contrast, provides no explicit incentive to spread out features. Empirically, we found that the L1 of norms version sometimes exposes phenomena of interest more effectively in the context of model diffing. Okay. In particular, it covers a mix of shared and model-specific features, while L2 of norms version uncovers only shared features. Okay. So,
Just one more thing. Just because the way this is trained with like the L1, L2 stuff, does it mean that all the problems that came with the SAEs before, like suppression or shrinkage or whatever they call it, when the feature magnitudes, when the reconstructions are systemically smaller than the actual activations, and then like feature splitting and like redundant features, like co-occurring features, all of those problems would transfer over to crosscoders?
I think in general, yes, but it sounds like they are arguing that it's not such a big deal because, for example, like you mentioned a few things. There was the feature splitting or the duplicate features. For example, instead of getting duplicated multiple times within each layer and then across all the layers, there's a single pool of features across the whole model. The idea is that it can generalize into them.
Yeah. But there could also be a feature that is learned redundantly, which is also spread across different layers. Like, what if the crosscoder just learns 5 different features, each of which is just like the same feature but spread across for one layer, for the other layer, for the other layer, and also learns redundancies?
Well, it's not going to learn things for each layer individually because all the layers are part of the input. So there's no reason that if you have 5 layers, if you learn it again 5 times, you could learn it once, twice, or 10 times. But I think the premise is that as long as you have the capacity, like it's sure you'll get some duplicate features in any, like I think they're making the case that the sparse autoencoders are a special case of crosscoders, right?
that it reduces to sparse to SAEs. Yeah.
I think it's probably worth to also take a look at the Gemma scope paper, where I think Neil's team kind of get into the reason why they use gated ReLU or like jump ReLU. So I think like on this paper, because they use L1 and ReLU, I think shrinkage can happen. But I think like if I remember correctly, like he probably write a tweet somewhere saying that like maybe like we can also try with like gated ReLU or even jump ReLU or like top K to see, because like they don't have like shrinkage. So yeah.
Yeah, that's a good point. I'll make sure to note that down. Okay, look at the Gemma paper. Okay. Okay. So when you do model diffing, you want to find features which are in both models and features which are in one model and not in the other model. And the L1 noise version lets you find something that is only in the okay. The L2 version more efficiently optimizes the frontier of mean squared error and global L0 across all layers of the model. Okay, so you might want to use a variant of crosscoders which uses the L2 of norms versus the L1 of norms if you don't care about like models behavior. Okay. So where it is not important to be able to compare loss values. Your charge is low. Do you mind getting a charger for this? Oh, yeah, I have the charger. Yeah. In this report, all experiments use the L1 of norms version. Okay. Crosscoder variants. The basic version above is what we'd call an acausal crosscoder. Many variants are in fact possible. In particular, several important dimensions are we doing crosscoders or normal SAEs? Do we want to have a setup where early activation predict later activations? Causality, okay? And locality, do we apply the crosscoder to all layers or just some? Or maybe apply them to layers from different models? Target, are you modeling the residual stream or layer outputs? Okay.
This
So
might be too big of a can of worms, but I don't understand what they mean. I think I understand what they mean, but I don't understand anything about how the cross model parts should work. Like the model diffing and that. Is it just, are we assuming that these are models of transformers with separately trained weights, but it's a similar structure?
can you explain that again? I didn't understand it.
So here they talk about that bullet point for locality. You apply the crosscoder to all layers of the sum, or maybe apply them to layers from different models. I don't understand how you'd be able to apply it to a layer of a different model. I mean, if you look, there's a couple of spots further up where they're talking about model diffing.
Oh, okay. So when you want to compare two different models, you can train a crosscoder on like a model which has like, so you take layer 3 of the base version of a model and you take layer 3 of the chat version of a model, right? Okay, and you can think of this and then you can say, let's say I take layers 1 to 3 of this model versus like of the base model versus layers 1 to 3 of the chat model. Okay, now what if you move the, so that instead you train your crosscoder on layers 1 to 3 versus let's say layers 5 to 8 of the chat model, right? Like, so you can do kind of this crosscoder, which is doing like a subset of the layers and then a different subset, which is comparing. Now, so versus one, which is this, okay, I'll do all of the layers of this model, which I want to compare to all of the layers of this model. This is what's happening. Like,
So why would, sticking to the different models, does it have to have the same architecture? Like if you have a chat version versus a document kind of base model? Is that what they're talking about? Or can you use this to compare the 3 billion parameter of llama to the 70 billion parameter of Gemma? Like, what do you, do they have to share some kind of?
I think you can do it with models from different architectures, yes. Okay.
Okay, yeah, okay, good. We can move on.
Yeah. But I haven't seen people training crosscoders on that, but I can look into that. Yeah. Are we modeling the residual stream or layer outputs? So far we are only modeling the residual stream. Is that right? Like in the acausal crosscoder, we weren't modeling the layer outputs. Because I think we were modeling the residual stream. Is that right? I'm not sure.
I think so.
Okay. So we got to set up early activation, pretty late activations. Following table summarizes the variance. Okay. Per layer SAEs, train a different sparse coder at each layer, which we have to analyze. Shared SAE, and this is very compute inefficient because you have to train an SAE for each layer. Okay. Same sparse coder used at every layer. This is the notion of features across layers with some features only existing as sublayers, but it doesn't allow features to rotate across layers, which we believe they sometimes do. I also think this is true, okay, because I've tried to do like rotation steering, okay. So I have to make a note of this, that, yeah, okay.
This rotation steering.
This is from the SAETS paper. They find that if you want to find an intermediate point between intermediate point between two different points, instead of taking like a similar average, you try to rotate between the 2 points.
Can you share that paper by any chance? Later on is fine too. I just don't know which paper you're referring to.
Yeah, I'll share now actually. SAETS. Okay. Only. Yeah, and this is the one. So I'll just share this archive link here. So they have a thing about rotation steering in here. Yeah. Right. So back to the Sparse Crosscoders paper. And then this is the focus of this entropic paper. Sparse coders interact with multiple layers, resolving cross-layer superposition and tracking features through the residual stream. Maybe one or multiple sparse autoencoders, and they may read and write to different layers. Okay. So each sparse coder both sees and predicts past, present, and future layers, often just one big coder. Features aren't anchored to a specific layer, convenient for analyzing which features exist and how they're distributed, but makes circuit analysis very difficult. Okay. Why does it make circuit analysis difficult?
Again?
I think that this makes circuit analysis difficult because you don't know how information is flowing. Like, I'm not sure why this makes circuit analysis difficult.
Because you don't have information about what's in this layer with this one. You're just looking basically at all the layers as one giant layer. It's harder to do. You do one layer.
Okay, which one makes the circuit analysis the easiest?
Look at those three on the causality. So the strictly causal is easiest.
Okay. So each coder sees activations from one layer and predicts only future activations. Best setup for circuit analysis when possible. Okay. Yeah, okay. So I think that I understand this a bit better now. So basically, if you want, this is like bidirectional attention versus like normal attention, where bidirectional attention might be worse for causality because future tokens can influence past tokens. Okay. So we don't want that. So
The weakly causal version just means that it's predicting the input as well as the future token. Versus the strictly causal is just taking an input and only predicting the future and not the input.
each coder both sees activations only and predicts both activations and temperature activation. It is if which feature is generally new and is more tolerant of features which can't be computed. Let me reread this. 1 second. Okay, it predicts. What features can't be computed? Like, I don't get this part.
Well, you look at the crosscoders, the autoencoders, they're really just trying to approximate an attention head using a linear layer.
Hmm.
Right? So there's the different architectures versus the full attention head versus the simpler model that you're using as the coder. The coder's not going to be able to learn everything. And so that's why they say that this weakly causal version, I think when they say more tolerant, the weakly causal version is more tolerant of, I think, compared to that acausal one that's just taking in all the layers at one. That's how I'm reading it. It might also apply to the strictly causal one, but the weakly causal one is more tolerant because it has its own input as its output.
Hmm.
That I'm not sure what this is like that. But
So what's the difference between the weakly causal and the acausal one?
the acausal just has all it's using future data that predicts past data in terms of the sequence of layers. Versus the causal ones are only using earlier layers to predict later layers.
So
The
it
acausal-
predicts the present and future, but it only sees present. Okay, so weakly causal is like, okay, I can only see the present now, but I can still predict. And
I think you can think of it as like weakly causal as like from one layer they try to predict what new features could be in like the following layers, right? Whereas like strictly causal, you only like use or like you only run it against that that specific activation layers, right?
Yeah, so strictly causal, each coder sees activation from one layer and predicts only future.
Yeah.
activation.
So strictly causal doesn't try to find any new features whatsoever, right? So or I guess like maybe like or maybe I'm completely wrong here. Strictly is basically just use what you've learned and only predict on like the future activations. Whereas like weakly causal, you can like figure out like if that specific features is new or not, right? So like strictly doesn't care if it's like a previous features that's already in like, you know, like the previous layers. Whereas like weakly, like you try to find like, oh, whether like this feature is new or not, right?
That's a good point. So I was reading it causal just in terms of like in a general sense that the past depends on the future. Or no, the future depends on the past, but the past does not depend on the future. I was reading it kind of with that interpretation, but you make a good point that when they say causal, it could also mean that this layer causes a feature to be introduced. And now I don't know which definition I'm thinking of.
Yeah, this part of the post is like the most confusing part to me. So whenever like I try to like think about this, like so yeah.
It's good that they got pictures and we're not just
Probably should reach out to Liv or maybe Chris to explain more about this part. So yeah.
yeah, I can also reach out to the transcoder author paper because I met him at NeurIPS. Jacob Dineski, I had dinner with him, so I can ask him about like what the heck is up with this causality and crosscoders. Yeah.
I mean, like the acausal one makes sense, right? Like in a sense, you just have like one big crosscoder and you interpret all the features, right? Makes sense. But the part of like where they train weakly causal and like strictly causal to like predict what's new and what's new, I felt like, can't we just do that with the SAEs? But like I understand like where they come from, right? Because like SAEs, Actually, now like speaking out loud, it sort of makes sense because like SAEs might get new features or not, right? Whereas like at a certain activation layer, a crosscoder can have one feature, and then the next one might have a separate like future features, right? So essentially, weakly causal, essentially you will use all of the like a priori knowledge and then try to predict, oh, maybe like this feature X could exist in the next layer. Whereas like strictly causal is basically like, oh, I only have, no, sorry. Now like when I speak it out loud, it actually even confused myself. Okay, never mind, discard all of that.
So I've written out, I think, at least where I'm confused. Is causality meant in the sense of output of the autoencoder or the coder only depends on earlier input, or the feature is introduced on this layer?
So output only depends on early input, or this feature is introduced in this. Okay. Yeah, I just noted that down in the Google Doc, which I'm using to track questions.
I think it might end up being that the two questions are equivalent, but it's
Let's move on. Locality. Okay, it should be smoother sailing from this point on. Yeah. Aaron, you're muted if you're saying something.
Oh no, I'm just kind of like speaking it out loud to try to like make sense, but yeah, don't worry about it.
Global. Each coder interacts with all layers except where constrained by the causality structure. Local. Each coder interacts with a limited window of layers. Skip layer. Crosscoders may skip layers to save compute. This doesn't work well with strictly causal models. And crosscoders may interact with layers from different models to create canonical feature sets between them. Okay, so yeah, this might be useful for models of different sizes. Okay. You know, that way, there's no way you can do all layers from one model versus all layers from one model because they have a different number of layers, right? So cross model makes a lot of sense to me.
Well, sure, but wouldn't it just be like all of the layers from model A and all of the layers from model B, and like, yeah, there may be different sizes, but that doesn't change the fact that you can still cross code between them.
No,
I don't
because
see any reason why they would have to have the same number of layers.
imagine you just have like one model, okay?
Yeah,
And then one model has one like big set of layers, okay? Which if you're doing an SAE per layer SAEs, you can just do per layer SAEs for all of the layers.
yeah.
But if you have two different models and you want to compare them, and one has a different set of layers, then you do per layer SAEs. How do you know which, like, so if you have like a model with like 5 layers, okay, when you look at layer like 3 of the smaller model, which like SAE are you
I guess
going
you
to like,
don't know,
which one, are you going to go to the middle one, or are you going to do like the number
Well,
3?
that's a solvable problem. You just say like when you, I don't think like for the crosscoders, you can do it between any two layers, right? So you would just decide, oh, let's look at the layer 10% of the way through on both of them.
Okay, so yeah, I also agree that it makes a lot of sense to look at like the relative position rather than like the absolute number of layers.
Yeah.
Okay, but this is one example of why, you know, crosscoders might be make it like easier because you're just looking at the features which are, you know, between them. Yep. That makes sense.
Yeah, I mean, like it seems like, yeah, there'd be a slight problem at the two model type different layers, but it seems like a very solvable problem.
Yeah, we can look at. I can look into this to by running experiments on like, you know, two different models with like.
Yeah,
features.
that would be interesting to
Yeah.
see if the results of those experiments.
Target, okay, they're predicting the residual stream and layer outputs, predicting the outputs before the added research. Okay, so this one I think is more of the SATS kind, and this one is more the this is like feels more normal to me. Yeah. So we have found both weakly and strictly causal crosscoders helpful for simplifying feature interaction graphs in our circuits work. Remain open questions as to how to faithfully validate these analyses. Note that strictly causal crosscoder layers as presented here cannot capture the computation performed by attention layers. Yeah, this is what was mentioned earlier over here, where it says that there's some layers, some things which cannot be done by attention, except some features which can't be computed, such as attention. Okay, so let's go back.
I have a quick question. Is there a way to also, I don't know what to exactly call this. It's not forgetting, but the exact opposite of like the causal thing that we're talking about, where there is a feature early on, but because of like redundant or noise information being added, that feature gets unlearned in the later layers and the model is not able to output the right thing.
So are you talking about, just to make sure I understand the question, like over here where the feature fades from the residual schema is actively deleted? Like this part of
Yeah, more or less, I guess. I was just thinking of the opposite case of like, what is the opposite of weakly causal, where there is a feature in an early layer and that is causally relevant later on, but the opposite. Maybe this is exactly what I was thinking, I guess. Yeah, I guess that was it. Thanks.
instead of being over here, you want to say, let's say you put it over here, so that over here the feature isn't represented. So like you cut that
Yeah,
over here, and
yeah.
then it's
So
and then it's no longer represented in this later layer.
yeah, but I'm just thinking of like, for example, the model, a specific example of some kind of hallucination. The model has seen a bit of the input training data that has caused it to learn some of the features, but it has not been trained on that particular data enough that it fine-tunes the whole model so that it is able to output the right thing. But that could be also because there's like noise features being added instead of like the actual ones, which could be deleted to mitigate hallucination. Does that kind of make sense? I'm just thinking of like what would be a practical application.
Okay, so you're saying that if you detect a harmful feature, okay,
Yeah.
with your crosscoder,
Yeah.
And then you want to update this, so do this like sort of conditional steering approach where you just add the vector if this feature is there, but if it's not there, then you don't add that vector.
Yeah.
Okay. I haven't tried this out, but I have thought about trying it out. Okay. I think that in practice, like what I've heard from some other researchers, but I don't know myself, is that this might have some risk of false negatives, where like it's hard to detect a feature unless it's like strongly represented. So you might miss a lot of the feature inside the resolution. But maybe it's possible to like detect it and then ablate it. Yeah. I know Fernanda would be interested in something like that. Yeah. Okay. So performance and efficiency of crosscoders versus SAEs. Oh, okay. Wait, do we skip something? Okay, no, we did skip this. We have found both weakly and strictly causal crosscoders helpful for simplifying feature interaction graphs in our circuits work, but there remain open questions as to how faithfully validate these analyses. Note that strictly causal crosscoder layers as presented here cannot capture the computation performed by attention layers. Okay, we reached this point. Some possibilities they're exploring include using strictly causal crosscoders to capture MLP computation and treating the computation performed by attention layers as linear. Okay. How would that work? Okay, so they use the strictly causal crosscoder, which cannot see the present, but it only predicts the future. They capture the MLP outputs, and then they treat that. Okay. This would require a lot of prompts, like, so this would be very expensive in practice. Like you need a lot of, okay, this is a prompt and this is the definition practice. Okay. Yeah, I'm not sure how this would work. This is confusing. Number 2, combining strictly causal crosscoders for MLP outputs with weakly causal crosscoders for attention outputs. Okay.
Isn't it so crazy if you can just replace the attention head?
What do you mean by replace the attention? Replace it with what?
Well, the way that they have the autoencoder, it's taking the input and trying to get the output. So if you have around the attention layer, if they actually scale it up enough, then it's possible that with the fully connected linear layers of the crosscoders would get close enough to actually be used instead of the attention head that it's trying to learn.
Your microphone is a little bit low. Could you try speaking up a bit to it?
Is that better?
Yes, that's much better.
Okay, super. So what I was saying is I was looking at bullet point 3, where they're saying that at least the way that I read it is that the crosscoder, which is really trying to take in the residual of before a layer and then compute the residual after a layer. If it gets good, it could replace the whole attention layer. And that would be interesting if you had that, like you just had an LLM that's just linear layers, because they were able to train these linear layers to be the autoencoders over the attention layers.
I think Connor Christine might have mentioned something that he was doing when he was training on attention layer outputs, like attention outputs. So maybe you can check with him. Yeah, I'm not sure if we understood the correct question.
Oh, just an observation.
Yeah. So cross-layer features, performance and efficiency of crosscoders versus SAEs. Can crosscoders actually uncover cross-layer structure? So they trained a global ecausal crosscoder on the rest of the activations of all layers of an 18-layer model. Okay. So Anthropic thinks 18 is reasonable. Okay. I think that 18 is reasonable as well. But maybe some places like might say 21 is reasonable. Okay. It's a joke about drinking ages. We compare this performance to 18 SAEs trained separately on the residual string layers. Use a fixed L1 coefficient for the sparsity. These are just technical details. Okay. They designed their loss to be comparable to a baseline SAE loss with the same L1 penalty as discussed above. They normalized the activations of each layer prior to training the crosscoder, so each layer contributes comparably to the loss. Okay, so they separately normalize. Yeah. They don't do it after. For each approach, they swept over the number of training steps and the number of total features. We select the optimal number of features at different flops budgets. Interested in how the dictionary performance scales with the total number of features in the crosscoder across all SAEs and with the amount of compute used in training. So for a model with L layers, a global ecausal crosscoder with F total features, the same number of total flops as a collection of per layer SAEs, which F layers each, F features each, and that's with L times F total features. Okay. So if you have a model with L layers and you have features greater than layers, then what are they saying here?
I think the next sentence answers your question, Or viewed another way, a collection of single layer SAEs with F total dictionary features summed across all the SAEs can be trained with L times fewer flops than a single crosscoder with F
Like,
dictionary.
this is what's confusing to me. Like, why do they use the same number of training flops? Like, the crosscoder
It's, yeah, I mean, we don't need to go deep here. They're just talking about if it's cost competitive, right? When they say flops, that's really just cost. So the question is it more economical to do 18 separate sparse autoencoders versus one bigger crosscoder with the same number of features?
could this be because of like cross-layer interactions having like, because you have like some features which might be spread across multiple layers, so the crosscoder is able to represent them more efficiently, right? So then why is
Yeah,
it
that's
the same?
that's exactly the question that they're trying to answer here.
Yeah,
So does the ability for a crosscoder to represent features that are spread across layers, is it worth it in terms of the extra cost of training?
Okay, so but if you made it instead of a causal crosscoder into like a causal or strictly causal one, would this continue to be true, or would this change? Like, what does it still use the same?
You can't make a causal, whether weakly or strongly, crosscoder that's as big as the acausal.
Oh, why not?
Well, just because you run out of inputs and outputs, right?
Oh,
The
right.
acausal is everything is an input and everything is an output.
But then you don't have as many inputs. Oh, yeah, okay, yeah, I get it. Yeah, that makes sense. Yes. Okay, thank you. Yeah, pretty good. I might need to go in around 5 minutes because I have a meeting early tomorrow. That is early, that like my meeting with Alyssa is like early in the morning rather than like it used to be in the afternoon, but she changed it to the morning. I just want to make sure that I sleep on time for that.
Yeah, no, I hear you.
So just like let's spend a few more minutes just wrapping up. Okay. I know that we're scheduled for until 8:30, but
It's okay. We can just kind of going quickly then. Scroll down a bit. We've got the
yeah, so this is one of the
the
plots.
charts. The big thing is that the crosscoders are 8 times more efficient and twice as expensive.
Right, so this is what I was expecting to see. Okay, so I was confused before because I said, wait, why does it use the same? But now they're saying that, okay, the crosscoders, the blue is the crosscoder, right? And the orange is the SAE? Yeah. Yeah, crosscoders dominate the per layer SAE. Wait, they're more feature efficient, but less flop efficient. Oh, okay, so this is surprising. So they use more training flops at over here, but then they're converging over here. Like over here, there's a big difference, and then they're like getting close. Oh, this is interesting. Yeah. So coders are overtrained, but you always overtrain. Okay.
I'm sure like because they use ReLU and different.
Just for the benefit of time, I would say scroll to the next chart and we can look at the paragraph after. That's kind of a good summary to the cost. Skip over this part and then look at the next chart. So the next one is it's the error for the crosscoders versus the per layer for a given number of viewed from this perspective, crosscoders provide dramatic benefits over per layer SAEs. By consolidating shared structure across layers, they exhibit a much less redundant and therefore more concise decomposition of the entire model's activation. In theory, the same consolidation might be achievable via post hoc analysis on SAE features, for example, by clustering features based on the similarity of their activations. However, in practice, this analysis may be difficult, particularly due to stochasticity in SAE training. Crosscoders effectively bake in this clustering and training time. Summarizing the results at a high level, the efficiency crosscoders and per layer SAEs can be compared in essentially two ways. In terms of the trade-off between reconstruction error and the sparsity of the features set used to reconstruct a single layers activity, crosscoders make more efficient use of dictionary features, but less efficient use of training flops. In terms of the reconstruction error versus sparsity trade-off in reconstructing the entire model's activity, crosscoders provide an unambiguous advantage by resolving redundant structure across layers.
Yep.
So to summarize, if you wanted to just get features of one layer, then the one layer SAE is better. But if you want features across the whole model, then the crosscoder is better.
Yeah, and I think refusal is an example of a behavior which is like, in multiple layers and rather just one. Okay.
There's an interesting chart if you scroll down to the next one.
Yeah. Here. Okay, so let's read this first.
We conducted some basic analysis of the crosscoder features. We were especially interested in the features behavior across layers. Do crosscoder features tend to be localized to a few layers, or do they span the whole model? And two, do crosscoders features decoder vector directions remain stable across layers, or can the same feature point in different directions in different layers? Addressing question 1, below we plot the decoder weight of the norms of 50 randomly sampled crosscoder features across the layers of the model, which are representative of the trends we've observed in a full collection of features. For each feature, so that's one of these lines, and each feature gets its own color there. For each feature, we rescale the norms so that the maximum value is 1 for ease of visual comparison.
Mm-hmm.
And so what they're doing is they've got a feature and they're tracing it through the layers of their 18-layer model in a way that I think is reminiscent to that the 13 versus the 3 circuits.
What do you mean
so
that
we don't have page numbers. So if you
the circuit picture with like the complicated circuit and the simple circuit.
Yeah. So the diagrams that we watched at the beginning where we were following theoretical features, I thought this was interesting because this is actually real features. So some real features only start towards that 10th layer and then shoot up at the end, versus a whole bunch of them are start on the first layer, peak on the second, and just kind of dwindle out. And then you've got.
I'm going to need to drop for now, so maybe you can take this. Okay, but
Hey,
so I have
so just gonna end it here, or
I think that Chris keep going over the rest of the paper for now.
I can take over. Smitty, do you have to go?
Please keep that sharing, okay?
no, I have all day.
Okay. Yeah, well, we can keep going. So let's see. The ability to track the presence of features across layers is spiritually similar to the results in transformative visualization via dictionary learning. Was this the one that we looked at before? I don't think so. I forget which papers I just looked at versus what we had presented, but I'm gonna take over the screen share, okay? Probably easier.
Yeah, do you stop sharing before that, or?
No, it's okay. And yes. All that, but let's just see. Do you see it?
Yeah, go through the part which is relevant to my project. So
All right. Okay, participants can see your application. Cool. So this is where we just were. And it's each of these individual colored lines, there's 50 of them, represents one feature as they traced it through the crosscoder, or I guess through the original model. We see that most features tend to peak in strength at a particular layer and decay in earlier and later layers. Sometimes the decay is sudden, indicating a localized feature, but often is more gradual, with many features having substantial norm across most or even all layers. I don't know how they did that with an acausal coder. That's okay. The ability to track the presence of features across layers is similar to the results from this other paper. We use dictionary learning to fit one dictionary that models activations at all layers of the residual stream. As far as we know, UNIL were the first to ask this question in the context of features. How do they differ? Conceptually, their approach considers a feature to be the same if it is represented by the same direction across layers, while crosscoders consider a feature to be the same if it activates on the same data points across layers. Critically, crosscoders allow feature directions to change across layers, feature drift, which we'll soon observe appears to be important. We now return to the second of our original questions regarding the embedding directions of crosscoder features. Below, for a few example crosscoder features, we show the strength of the features decoder. Let's just see. Below for a few, we show, okay. Below for a few example crosscoder features, we show a top and a bottom, the strength of the features decoder norm in each layer as above, the layer in which the feature strength peak, and the cosine similarities between the features decoder direction in that peak layer and all other layers. Bottom, the projection of the features decoder vector layer I onto its decoder vector direction, its decoder vector direction in layer J, thus the directional each plot indicates the norm of the features. Okay.
So I guess we're looking at some plots there. And what's the on the bottom one? What are the axes? I see the bottom is, I guess, the coded direction, but what's the other axis? The what's the y-axis there?
So these are the two the pairs that we're looking at. So the bottom ones, the projection of the features decoder vector in layer I onto its decoder vector direction in layer J. Thus, the diagonal of each plot indicates the norm of the features decoder vector in each layer. So it's comparing the way that they look at features in this paper, which they said crosscoders consider a feature to be the same if it activates on the same data points across layers. That was oh no. Oh, yeah, so that's all that this is. I thought it was comparing the way the UNIL paper was doing it, but it's just their paper looking at a single feature in different ways. So the decoder norm magnitude versus the cosine similarity of decoder to its peak by hey,
Yeah, I'm back.
we got some plots. I think the point is it's just showing how we don't need to dive too deep into how these are calculated. It's just they're monitoring individual features through all, I guess, 18 layers, 0 to 17. So each of these three pairs are example features. Sometimes it's relatively all throughout the model, I guess. So the feature rotates and magnitude shrinks. Magnitude shrinks faster than feature rotates. Feature rotates but maintains magnitude. So yeah, you can, I guess I don't let's see. These examples are selected to illustrate the range of feature archetypes we find. Below, we show this information for 36 randomly selected features. So here, yeah, they're just watching features being able to rotate versus increase and decrease in magnitude. So the blue is magnitude. The orange is cosine similarity to see how much it rotates. So it's kind of interesting.
Yeah, I'm on the same page.
So this is 36 examples of those plots, just to get a sense of the variety.
Oh, I think it's just Smithy, me, and you right now.
That's right. I mean, there's a live stream, so who knows who could be watching us online.
Yeah, she don't have to go too, so we'll get back in touch and organize everyone. But overall, we find that most features decoder directions are much more stable across layers than would be expected by chance, but also that they drift substantially across layers, even in layers where the feature decoder norm remains strong. The specific behavior varies considerably by feature. This suggests that the cross-layer features uncovered by our crosscoders are not simply passively relayed via residual connections. Yeah, no, I mean, that makes sense. It's no, we do not. Yeah, these are anecdotes. Okay. All right, so that was all with the acausal. I would imagine the locally masked convolutional variance in which each variant. So now we're getting into the causality and locality. Yeah. Let's see. We experimented with locally masked convolutional variants of crosscoders in which each feature is assigned a local window of k layers that is responsible for encoding and decoding. We hope that this would allow us to capture the benefits of crosscoders while minimizing the flops expense at crosscoder training time. However, we found that eval loss interpolated fairly linearly as we varied the convolutional window for window k from 1, the per layer SAE, to n, the global acausal crosscoder. There is no obvious inflection point that optimized the performance cost trade-off. Put another way, the performance of a locally masked crosscoder was similar to that of smaller flops matched global crosscoder. This is consistent with the picture for the distribution of features across layers as seen in the previous section. So that, I think, answered your question, Abdur, before about using the smallest case is the sparse autoencoders. The biggest case is the acausal, because that's every input and every output. And then they said, I think we also experimented with the weakly crosscoders. We found in particular on an architecture in which each figure is assigned an encoder layer I. Its encoder reads from layer I alone, and its decoder attempts to reconstruct layer I and all subsequent layers. We found in terms of eval loss performance, this architecture swaps efficiency is in between that. With respect to dictionary size, its performance lagged behind that of global crosscoders by a factor of 3 to 4. And these were some of the feature decoder norms for features with different encoder layers. So yeah, I mean, I guess at layer, no. I was about to say that for layer 1, the weekly causal crosscoder is the same as the acausal, but it is not, because it only the weekly causals only have one input, so that's fine. One interesting pre-post MLP. Oh, this was about whether it was the model, the layer output versus the residual. One interesting application of crosscoders is to analyze the differences in feature sets before and after an MLP layer, and the computations that give rise to new features in the MLP output. To achieve this, we can train a crosscoder on the pre-MLP residual stream space and the outputs that the MLP writes back to the residual stream. We use a masking strategy in which features encoders read only from the pre-MLP space, but their decoders attempt to reconstruct both the pre-MLP activity and the MLP output. Note that this architecture differs from a regular transcoder in which the features are only responsible for reconstructing the MLP output. This architecture has two nice properties. First, it allows us to identify features that are shared between the pre and post MLP spaces and features that are specific to one or the other. Yeah, to see this, we can plot the relative norms of the decoder vectors within each space. Remarkably, we see a clear trimodal structure corresponding to pre-only shared and post-only newly computed features. Interesting. To see this, between the pre. This part that they're talking about here was these, the target. So they're the modes, I suppose, are one residual input. The layer output, I guess, would be the other side, and the shared would be the residual stream output. I'm not super confident on that. Second, because we constrain the encoder vectors to live only in the pre-MLP space, this architecture allows us to analyze how these newly computed features were computed from the existing features in the residual stream, similar how to one would analyze a transcoder. In particular, the inputs to a newly created feature can be computed by taking the dot product of the downstream feature encoder vector with the upstream features decoder vector. In particular, the inputs of a newly created feature can be computed by taking the dot product of the downstream features encoder vector with the upstream features decoder vectors and weighing by the source features activation, either in a particular context or averaged over dataset examples. Isn't that what attention does, roughly? Maybe not. I don't know. It sounds like there's a parallel, but anecdotally, we often find that the post-MLP feature represents a more abstract concept.
Tokens, not over features, right?
Hmm?
Attention operates
That's
like
true.
it's a
Yeah.
EQV over, you know.
Yes. All the
I don't know how to like.
is yeah. Oh, okay. We introduced crosscoders as a way to understand cross-layer features, but the same approach can be used to extract cross-model features. I think this will answer my question from earlier in a bit more detail. In this section, we'll study the use of cross-model features to compare and diff models. Our results here are very preliminary. While there are significant signs of life, we find that this strategy produces many features we don't understand. Let's get the background. One of the exciting things about, okay, hold on, let's just bullet point this. There's a long history of research seeking to compare neural networks, of course, comparing the functional differences of different neural networks, for example, measuring the performance of benchmarks is a central part of machine learning paradigm. But it's natural to ask deeper questions. How do the representations compare? How do they compare mechanistically? A host of methods have developed attempting to address these questions. We can divide them into a few categories. Entire representations. So this is, yeah. We can look at finer grained neurons and features. We can look at other things, although the existence of universal features and circuits Yeah, okay, so other things like universal features and circuits. You just, as the idea of universal first became widespreads, the idea of diffing models as a way to make safety auditing easier. Comparison. All right, let's see what they actually did here. That's just background. What kind of comparisons are possible? One of the exciting things about crosscoders is they're not limited to closely related models, such as a fine-tuned version of a particular base model. Instead, we can get cross-model features between any models, including across training snapshots, fine-tuning, different training runs, dataset changes, scaling, architectural changes, adversarial training, equivariance. Past work has studied the extent to which representations are equivariant by comparing the representational models to the representation produced from transformed inputs, essentially treating them as different representations and finding maps between them. This isn't limited to 2 models. Subject to computational constraints, we can get cross-model features between arbitrary number of models. Amazing. Of course, when models are significantly different, we may not know what the analogous layers to compare between the models are. In this case, we may wish to also have our crosscoder extend across layers. That makes sense. Once we get cross-model features, we can study features at comparison, the circuit comparison, and the differences in feature geometry. That's kind of an interesting question. We trained a crosscoder with 1 million features on the residual stream activations from the middle layer of Claude 3 Sonnet and the base model from which it was fine-tuned. We wanted to test whether the crosscoder could decompose the model's activations into shared features and model-specific features. These model-specific features would indicate features learned or forgotten during fine-tuning. To test this, we looked at the relative norms of feature decoder weights in the 2 models. Remarkably, we found that features cluster in 3 obvious groups: base model-specific features, fine-tuned model-specific features, and shared features. In this example, there are between 4,000 and 5,000 model-specific features for each model out of a total of 1 million features.
If you look at the crosscoder like model diffing reproduction notebook, I can send that in this chat, and you just like scroll down to the bottom of that, you'll see the same thing. So maybe this will be good for recording. Can you open this notebook?
Sure. Yeah. Okay, you said scroll down. This?
Scroll down to the bottom, yes.
This one?
Yes,
Further?
you can see it's similar to the one
Oh,
which
yeah.
was there earlier. Yeah. Okay, so if you want to, play around with that, this is and at the very bottom they compare like the base versus the chat, which is something that I found interesting.
Just so broken in Firefox. We notice 3 main clusters representing Anthropic's results. Base specific, yeah. Yeah.
Is this the same? Is Sonnet 3.0 the same as the 18 feature, like the 18 layer model they were mentioning earlier, or is it different? I don't think Sonnet 3.0 is the same as the 18
I
layer.
don't think I would assume it's different.
Yeah,
I don't think they.
surprised if like Sonnet had only.
I don't think they passed the number of layers in the block, so if they said that it's it can't be the same as the one we know has 18 layers.
Yeah. Hmm. The interesting thing they haven't talked about is that the features they are identifying are by definition only in their training corpus for the coder. It'd be interesting to see what they actually have in there, because clearly stuff like, can you help me build a bomb, is in there. And all of these things, these all have to be examples of things that are there. But there's also lots of features that are not immediately interpretable either. I guess this aligns that. Oh yeah, okay. So this is model differential in overscale. We trained an acausal crosscoder on 10 evenly spaced layers from 3 models of increasing sizes. We were interested in how much shared structure exists across different models and which layers correspond to which across models. Our analysis is in very preliminary stages, however, we have obtained one interesting result. That's what they did. The example below shows the result of running.
NMF. What's NMF?
I don't know. That's not really. For each feature, we measured the norm of its decoder in each layer model pair, producing a 3.
Non-negative matrix factorization. That's the NMF.
Where is it?
Like we then applied non-negative matrix factorization. That's obviously what NMF means.
Oh, okay. Yeah. Yeah. So the example below shows the result of running non-negative matrix factorization with 4 components, assigning a different color to each component left, and the spectrum of feature loadings onto each component right. Right. Roughly, one of the components covers the early layers of all models, and another covers the later layers of all models. The other 2 components cover the middle layers of the smallest model and the larger 2 models, respectively. This suggests that qualitatively, new representations emerge in middle model layers as model scale increases. We are interested in qualitatively exploring the features responsible for these differences in future work. Yeah, okay. So the way I'm reading this is features that show up early in the small models also show up early in the large models. Features that show up towards the middle of the medium model also show up towards the middle of the large model. And this last one that shows up later, and all of them show up later. Yeah.
Okay, we've almost reached the end of the paper. I don't think we'll have time
Yeah.
for that. Yeah, let's just finish this.
Do we want to go over these?
Questions is fresh traction. Okay. Yeah.
All right, let's see. So these are kind of some future questions. How do features change over model training? When do they form? Do they form abruptly or gradually grow? That would be kind of cool. That would be. Sure. Why don't you screen share?
You said. So you're here, right?
I don't see your share.
Oh,
Try it
why
again.
not? Okay, let me try again. Share.
There we go. Yeah.
So how the features change over model training when they form, from abruptly or gradually grow. Do the directions drift over training or have a relatively fixed direction early on? If you train a model twice, directions do you get a features? Okay. This is very important, to see like, do they learn like universal features, right? Yeah, but I think there's going to be some difference, but like, it's interesting to see, okay, fine, if it has the same loss, does it also have the same features? Yeah. Or like other features all rotated or something.
And when they say model and training, I assume this is over the base model, not the coder model.
I think this is not about pre-training, but it's also interesting because, like, if you look at post-training, like if you do RL over a certain like data set, like in the alignment thinking paper they did this, then it might still be like there's some sort of brittleness. Yeah. Okay. I gotta get out of the Uber now once again, but that's okay.
Okay.
Yeah, I gotta go, but thanks.
Yep. I think we're just about done here.
Thank you.
So yeah, these were some other future questions. I think we're good. One might see the transition from interpreting neurons to SAE or transcoded features to crosscoders as progressively moving away from the literal surface level model that we were studying. Each step of abstraction allows us to escape unfortunate details of how circuits may be scaffolded into models, but at the cost of moving further away from the ground. Oh, it's unfortunate, but if we set things up carefully, in particular using error features, we can reason with these abstracted versions of models as a kind of exact isomorphism within the original model, in the sense that they predict the same activations at every layer as the underlying model. But there could still be downsides. Crosscoder errors may be important and extremely difficult to interpret. Yeah, more aggressive isomorphisms may complicate how causal structure maps to layers. Some notion of mechanistic faithfulness seems important, but it's not yet clear how to formalize it. Despite these downsides, it is quite plausible that the interpretability advantages of studying simplified isomorphisms to the underlying model will be significant enough to favor this approach. Yeah, no, it's cool. It is. I've always kind of wondered why SAEs picked a specific layer. Like we talked about a few papers where they just picked, I don't know, a layer that's 2/3 of the way through the model. And this seems like a much more robust way of trying to do interpretability. So with that, Abdur, thank you for suggesting the paper.
Yeah.
Thank
Fantastic.
you, Smitty, both for staying through to the end, and we'll catch you next week.
Bye.
All right, thank you. Bye now.